Hello everyone, this is a video demo for my Applied Deep Learning projects. So for this project, I utilized for tumor slides, tumor 110, tumor 084, tumor 091, and tumor 078. And this is the visualization for all four slides, how they look like. And there are some statistics for each tumor slides. So for instance, for tumor 110, 31% of the slides are tissue patches. So I defined the tissue patches to be those patches have over 50% of the pixels are tissues. I set the cutoff line to be 50. Only those patches have 50% of have over 60% tissue percentage will be considered as the data points. Otherwise, those patches would be ignored. And among that 31% tissue patches, 59% of those patches are cancerous, have cancer in it. So, and I did the similar statistics for all the other tumor slides. After that, I extracted those patches from the slides. I selected the dimension level to be 3. At the same time, the downsample factor would be 8 at dimension level 3. Patch size to be 100 times 100. And the reason is that because I want there would be enough data points ended up to build up the models. And the cutoff line to be 50% as the tissue patch percentage. And after that selection and filtering procedures, there ended up to be over 10,000 patches. Then I do train test validation split. 64% of those patches to be trained data set, and 16% are validation, 20% are test. Then I do the data augmentation to the trained data set only, because I want there are twice the amount of original trained data set. I do the rescale, rotation range set to be 40, width shifter range to be 0.2, height shifter range to be 0.2, shear range to be 0.2, zoom range to be 0.2, horizontal flip to be true, and field mode to be nearest. Then I also do the same rescale operation to validation and the test data. Then I started to build the model. Instead of what the paper proposed to use Inception v3, I used VGG16 as my convolutional base, plus the dense layers. And I would show the dense layers architecture. Here it is. There are over 3 dense layers, and except the last output layer, for these 2 dense layers, there are also dropout layers in it to avoid overfitting. At the last dense layer, there are only 1 node, and the activation function to be sigmoids, because this is a binary classification problems. And the model's optimizer is RMS propagation, loss to be binary cross entropy. I let the model to fit for 15 apples in order to overfit too much, and the batch size to be 50. I also introduced a parameter called class weights, because in my case, there are way negative patches, which does not have tumor in it, over the patch has tumor in it. So I assign 0.8 to negative patch, because that's our majority class, and a 1.2 to minority class, which are positive patches, have tumor in it. Then the model trained for 50 apples, which I said before. I evaluated the model's performance on test and achieved 0.9 accuracy. And I also plotted the training and validation accuracy for 50 apples, as well as the training validation loss for 50 apples. Then you can tell the model itself does not overfit too much. Then I evaluated the model's performance on both old slide and new slides. What I mean by old slide is those slides I used it to extract the patches and use those patches to build the models. New slides are those slides the model never seen before. I used a precision and a recall as my evaluation matrix. Precision here is defined by the number of true positive patches divided by the number of positive patches predicted by my model. And recall is defined by the number of true positive patches divided by the number of positive patches by ground truth. And here is the results. This is the evaluation results on old slides, tumor 078, which I utilized to extract the patch. So here, 28% of the original slides are tissue patches. And among those, 45% those patches are cancerous. And here's a visualization overlay the mask on the tumor imaging slide. For this case, if the model's predicted probability is over 0.5, the results will be the patch will be considered as a tumor patch. Otherwise, this patch is tumor-free. So for that, the model achieves the precision to be 0.85 and achieves the recall to be 0.84. F1 squared is 0.84. I'll also overlay the predicted results over the true tumors imaging slide. And here's a visualization. Then I evaluated the model's performance on a completely new slide, which is tumor 016. And it achieves the precision to be 0.82, recall to be 0.68, F1 squared to be 0.74. But however, compared with the ground truth slides on the left, the predicted slides on the right, it has some missing patches in this region. In addition, I also evaluate the model's performance on tumor 064. And by ground truth, 40% of the original slides are tissue patches, and among that 17% of those patches are cancerous. And here are those regions. And my model's performance on this tumor slide, it achieves the precision to be 1 and recall to be fairly low, 0.07, and the F1 score to be 0.14. And here is a visualization for the predicted results. I think the reason the model does not perform that well on this tumor slide is because in the original slide, there are very few patches are actually cancerous. So that's made the models has a hard time in prediction. And that's all I did for this applied deep learning projects. Thank you so much for watching.